Hello, welcome to another module in this massive open online course. So let us continue our discussion on this DTMCs, discrete time Markov chains, and let us look at the limiting behavior of a DTMC, discrete time Markov chain. Okay, so we want to look at the limiting behavior of limiting behavior of DTMC. We will start with our so what we will do, let us look at xn, which is the state of the DTMC for n greater than equal to 0. Remember, this is our time and this is basically our xn is our state. Now, we would like to ask the question, what is the probability xn equal to Si as n becomes very large, as time, that is time is extremely large. That is, after a long period of time, if you observe this probability is the probability that the state is Si. Can you comment about that? Can you comment about that? Can you comment about what is the probability that the state will be in Si after a long duration of time n? Okay. Now, let us use this. Let us use an example to understand this better. So, for instance, consider our industrial reliability problem, where you have the machine which has two states, operational and faulty. Consider now, what we have here is, if you look at the one step or the transition probability matrix, this is basically your 0.95, 0.05, 0.9, 0.1, and now if you look at p square, this is going to be 0.9475, 0.9450, 0.0525, 0.0550, and we know that p square gives the two step transition probability, that is probability xn plus 2 equal to Sj given xn equal to Si, that is the element Pij. Okay. So, these are the two step transition probabilities. So, I hope all of you also appreciate that. So, these are the two step transition probabilities. Now, let us look at p to the power 10. This gives the 10 step transition probabilities, and you will observe something interesting. So, you will observe that this is 0.9474, 0.0526, 0.9474, and this is also what you starting to observe is that both rows are the same. That is, if you look at the transition probabilities, you will observe something interesting, that is, in this matrix, the 10-step transition probability matrix p raised to the power of 10, both the rows are same. And further interestingly, now if you look at p 20, what you will observe is that this is again essentially it is the same matrix. So, P 20 approximately equal to what you can see is it does not change significantly. There might be some minor numerical variations, but you can see by and large they are the same, and therefore, you can say this is basically the limit n tending to infinity p raised to the power of n, that is the n step transition probability. And if you call this as the vector pi bar, that is, you call this as pi 1 and you call this as pi 2, what you can see is essentially this is your pi 1, this is your pi 2, and what you can see is this pi 1 or this pi j equals probability x n, or you can even say this probability x n equals S j given x 0 equals S I, that is the starting state can be the starting state is S I, and you can see this is the same, all the rows are same, implies this is the same for all S I, right. So, this probability is same for all S I, that is irrespective of the starting state. And this is what you would expect, because at time n equal to infinity, it does not really matter which state you have started from, right. The probability that is in state S j is same irrespective of the starting state S I, and this is what we are denoting by pi j, right. So, this is what we are denoting by pi j. So, pi j equals probability x n equals S j given x o equals S 1, this is equal to probability x n equals S j given x o equals S 2, so on. This is the probability x n equals S j given x o equal to S n. So, essentially this does not depend on the initial state. Does not depend on the initial state, which is a very interesting property. Further, now if you look at the limit n tending to infinity, now if you ask the question what is the limit n tending to infinity, probability x n equal to S j, that is at n equal to infinity, what is the probability that this discrete time Markov chain will be in state S j. There is a very simple way to evaluate that, that is probability limit n tending to infinity summation over all I probability x n equal to S j given x naught equal to Si times probability x naught, the initial probability x naught equal to Si. Now, we have seen this quantity is essentially pi j for all j, this quantity does not depend on I. So, this becomes, and now if you take the limit n tending to infinity, now first let us take the limit n tending to infinity inside. So, this becomes summation over I limit n tending to infinity probability x n equal to S j given x naught equal to Si times probability x naught equal to Si. This becomes over I probability x n equal to S j given S naught equal to Si. This becomes, this is your pi j, remember this is essentially your pi j times probability x naught equal to Si, and now you take this pi j outside, this becomes summation over I probability x naught equal to Si. Now, this sum of all probabilities is equal to 1. So, this becomes equal to your pi j. This probability x naught equal to Si for different I is nothing but the probability density function or the probability mass function of the initial distribution of the state probabilities. And what this shows is limit n tending to infinity, and this shows a very interesting result, that is after a very large time, if you ask the question what is probability x n equal to S j, this is equal to pi j, and therefore, this is known as the stationary, and this is basically, therefore, this is essentially what this is. So, the probability at n equal to, so the probability at after long duration, that is, and this is irrespective of the and the interesting thing is this is irrespective of probability x naught, that is irrespective of the initial probability distribution or mass function, probability that x naught is in state Si. After a very large duration, probability x n, that is limit n tending to infinity, the probability that the discrete time Markov chain x n discrete time Markov chain can be found in state S j equals pi j, where remember pi j is basically the jth element of any row of the n step transition probability matrix as the limit n tends to infinity. Okay. So, that is the interesting. So, this is essentially what we call as the limiting behavior. This is the limiting behavior of Dtmc as n tends to infinity. Now, we have the notion of what is known as a stationary distribution. For any Dtmc, we also have what is known as the stationary distribution, which is again a very similar concept. We have this notion of a stationary distribution, which is essentially that what is the stationary distribution. Now, if you look at this, let us start in the distribution. So, let us start in the distribution pi bar equal to pi 1, pi 2 up to pi n, that is these are where pi I equals probability that x n equal to s, the probability that x naught equal to s I. This is the probability that x naught equal to s I. Then what happens is, now if pi bar transpose times p equal to pi bar. Now let us consider a probability distribution. Probability distribution, this is the probability mass probability distribution for the initial state, right. So, the start with the distribution. So, distribution for the initial state. Now, if pi bar transpose p equal to pi bar, this implies that if you look at any ijth element, this implies pi I, this implies that pi I p pi I, or this implies that pi j, or this implies that pi I times p I j equals pi j, all right. Pi I times p I j equals pi j, where you have I equal to 1 to n. This implies that if you remember summation I equal to 1 to n, this implies that probability the probability x naught equal to s I times probability, the transition probability x 1 equal to s j, x 1 equal to s j given x naught equal to s I equals pi j, but this is nothing but initial probability of x naught equal to s I times the transition probability that it from x naught it transitions to x 1 equal to s j summed over all possible s I. So, this is the probability of transition probability. So, this is probability of s I to s j summed over, and this weighted and summed over the probabilities of all s I, and this equal to p j, and this is nothing but essentially if you look at this quantity, this sum, that is this summation over the initial state s I multiplied by x 1 equal to s j given x naught equal to s I. This is nothing but the probability that x, this is from the total probability rule, this is a probability that x I or x 1 equal to s j. Because the probability x 1 equal to s j, you can write it as follows. If you look at probability x 1 equal to s j, probability x 1 equal to s j is the summation, you can write it as the summation probability x 1 equal to s j intersection x naught equal to s I over all possible states or all possible I. This basically follows from the total probability rule. Which is basically equal to nothing but summation over I probability x 1 equal to s j given x naught equal to s I times probability x naught equal to s I, and that is essentially what we have here, and that we can see is equal to now from this property of this vector, that is now equal to pi j. Therefore, what it means is, if pi bar transpose p, if you find a vector pi bar transpose p equal to pi bar, this implies that if we start with or when we start with probability x naught equal to Si equal to pi I, we will end up with, if you look at this, probability x1 equal to Sj equal to pi j, this implies that probability x1 equal to Si equal to pi I. So, this implies that when we start with, we have probability x1 equal to Si equal to pi I. Similarly, probability x1 x2 equal to Si will also be equal to pi I, and so on and so forth. Probability any xn equal to Si equal to pi I, and therefore what this means is, this is basically, this is stationary. The probability that xn equal to Si does not depend on n. So, this distribution is a stationary distribution. So, if you start with the distribution pi bar, that distribution remains for the states at the next possible time instant, at the time instant after that, and so on. So, this is distribution, this pi bar is a stationary distribution. This pi bar is a stationary distribution, that is, does not change with time. This does not change with time, and when does that happen? This happens with, remember, pi bar transpose p equal to pi bar. This implies pi bar is a left eigenvector. Pi bar is a left eigenvector of p. Pi bar is a left eigenvector of p, and remember, the eigenvectors, they can differ by scaling. Now, to make it a probability mass function, we have to ensure that it sums to identity, and summation over I pi I equal to 1. That is, what we do is find the left eigenvector of p such that summation of the individual elements is equal to 1. That gives you the stationary distribution of the Dtmc. So, this pi bar is a stationary distribution. This then becomes a the stationary distribution of the Dtmc. Example, if you take an example, if you take a look at, again we go to our industrial reliability example, which is our p equal to 0.95, 0.05, 0.90, 0.10. You can say, so you can either say this is left eigenvector of p, or if you take the transpose, you can also write it as p transpose pi bar equal to pi bar. This implies that right eigenvector, or we simply call this as eigenvector of P transpose. So, now take eigenvector P transpose and find what we asked to the question, what is the eigenvector this is equal to, you can see once again not very surprisingly this is basically 0.9474 0.0526, which is nothing but the first row of P n as n tends to infinity, same as the limiting distribution by, and this is by and large true, this is same as the limiting distribution, that is this is the eigenvector such that eigenvector of P such that, remember eigenvector of P such that sum of elements is equal to 1. This is an important property to keep in mind, eigenvector of P such that, remember you cannot take any eigenvector because it is a probability distribution function, probability mass function. So, sum of elements must be equal to 1, otherwise it is not a valid probability mass function. So, eigenvector of P such that sum of elements such that the sum of the elements equal to 1. Okay. Right. So, this is the same as the limiting distribution and that is essentially what you find. So, this is a very interesting aspect of the discrete time Markov chains. What you find as P tends to n, that is for a very large duration, as P tends to n, that as n tends to infinity, P n, that is the n step probability transition probability matrix approaches a matrix which has a structure that all the rows of this are identical. Each row of that then gives the limiting distribution of the Dtmc, that is the probability that after a large time instant the state x after large duration n, the state this xn, the Dtmc, the state at time instant n is basically sj, that is basically pi j. And what we have seen is that this stationary this limiting distribution also corresponds to what is known as the stationary distribution, that is the Dtmc starts in this initial distribution of states, initial probability distribution of the states that remains unchanged for any n, and this stationary distribution can be found as the left eigenvector of the transition probability matrix P. So, this is a very interesting property of the Dtmcs and its relation to linear algebra, and you can see, as you can see, linear algebra plays a very important role with matrices, products of matrices and so on, and the eigenvectors, it plays a very important role in the analysis of Dtmcs. Alright, so let us stop here and let us continue in the subsequent modules. Thank you very much.